Hi folks! The following video is going to talk about SN2 and SN1 substitution reactions. I'll be discussing mechanisms, kinetics and rate laws, stereochemical outcomes, and solvent effects. The discovery of mechanisms for substitution reactions began in some early investigations of quaternary ammonium salts being reacted with hydroxide. In these ammonium salts, 3 groups on the nitrogen are methyls and 1 is an R group that is being varied. In one set of experiments, this ammonium starting material, featuring a 10-carbon chain, was treated with hydroxide, and what was observed is that methanol was produced, and an amine still featuring the 10-carbon chain and 2 of the methyls was generated. From kinetics experiments, it was determined that this reaction was first order in the ammonium electrophile and first order in the hydroxide nucleophile. In a second experiment, the R group on nitrogen was varied and was replaced with a carbon attached to 2 phenyl groups. This was again treated with hydroxide, and in this case, the alcohol was formed with the carbons on the right side of the molecule rather than one of the methyl groups, and trimethylamine was produced. In this case, the reaction was determined by kinetics experiments to be first order in the electrophilic ammonium salt, yet 0 order in hydroxide. So these fundamental experiments exposed a couple of things. 1, the group of the ammonium salt that reacts varies between these 2 different studies, and the kinetic behavior varies as well. From studying a whole range of ammonium salts, the authors found that the reaction is always first order in the ammonium electrophile, and they find that in terms of the nucleophile there is more variation. In some cases, the reaction was first order in nucleophile, and in other reactions it was 0 order with respect to nucleophile. This provided an initial indication that multiple substitution pathways must exist. SN2 refers to the bimolecular nucleophilic substitution reaction. SN2 reactions can involve alkyl halides that are either primary or secondary. Tertiary alkyl halides will not undergo these reactions by this mechanism, and they typically involve good nucleophiles. Here's an example of an anionic ethoxide nucleophile. In the SN2, there is simultaneous nucleophilic attack and loss of the leaving group. This would generate an ether product with a new carbon-oxygen bond. Notice that upon the substitution reaction, the anionic oxygen is converted into a neutral oxygen. SN2 reactions can also occur involving strong nucleophiles that are neutral, such as amines. In this case, I'm showing a neutral ammonia molecule reacting with chloroethane in an SN2 reaction to generate an ammonium salt. So upon the substitution reaction, the neutral nitrogen was converted into a cationic nitrogen. SN2 reactions can also occur between resonance-stabilized anions. For example, in the following enolate, this carbon lone pair is in resonance with the adjacent carbonyl. In this particular SN2 reaction, it is this nucleophilic carbon site that will behave as the nucleophile in the SN2 step. I can show this reaction by bringing a lone pair down from oxygen, using the pi bond as a nucleophile, and breaking off the iodide leaving group. The effect of this SN2 reaction is that a new methyl group has been added adjacent to the carbonyl to generate a longer chain ketone. So in all of these example reactions, I'm using a strong nucleophile, which could either be anionic or neutral, and the alkyl halide is either a methyl group, primary or secondary. We can consider the kinetics and rate law for the SN2 reaction. Here I'm drawing a general alkyl halide reacting with a nucleophile in a single step to give a substitution product and a halide anion. This concerted reaction would have a rate law dependent on the rate constant K, the concentration of the alkyl halide, and the concentration of the nucleophile. So we would expect to observe second-order kinetics. Often to promote the substitution reaction, these reactions are run with an excess of nucleophile. And when this is the case, if the concentration of the nucleophile is much higher than the concentration of the alkyl halide, the reaction won't use very much of the nucleophile, and that concentration is approximately constant. Under these conditions, I'm going to start by moving that concentration of nucleophile term toward the front of the rate law. And the rate constant K is a constant, and if we have a large excess of the nucleophile, this concentration behaves as a constant as well. I could lump this concentration of nucleophile term in with the rate constant and define a new term K-obs, the observed rate constant, where K-obs is equal to the actual rate constant times the concentration of nucleophile. Notice that the alkyl halide term is unaffected by this. These conditions, with a large excess of nucleophile present, give us pseudo-first-order kinetics. So my rate is still dependent on one concentration term to the first power, and everything else has been combined into the observed rate constant. SN1 reactions are going to be unimolecular nucleophilic substitution reactions, where unimolecular is just referring to the rate-determining step. Here's an example alkyl halide where the alkyl halide is secondary and benzylic. This alkyl halide could undergo a loss of leaving group step. This would generate a carbocation intermediate, which is secondary and resonance stabilized. This carbocation is a strong electrophile, and it could be trapped in a nucleophilic attack step. Here I'm showing a methanol solvent molecule acting in this role. In the next intermediate, a new carbon nucleophile bond has formed, and if a neutral nucleophile was used, the atom attached to carbon is now cationic. To get to a neutral final product, a proton transfer is necessary. A solvent molecule could act as a base in this proton transfer step, and this would generate a neutral final product. If in the SN1 mechanism the carbocation intermediate reacts with a solvent molecule, this is known as a solvolysis reaction. Electrophiles that generate tertiary carbocations or resonance-stabilized carbocations are typical of these reactions. And the nucleophiles in SN1 reactions could either be anionic or they could be neutral. Often it will be a neutral solvent molecule that acts in this role. For deriving a rate law, we can consider two steps as being critical. First, the loss of leaving group step to generate the carbocation intermediate, and then that carbocation's reaction with nucleophile to give the substitution product. Here I'm not worrying too much about the identity of the nucleophile. Note that if it had been neutral, you would need a final proton transfer in order to get to a neutral final product, but I'm going to ignore any proton transfers that may occur at the end of the mechanism, for simplicity in the rate law. Using the steady state approximation, which is the assumption that the concentration of the reactive intermediate is constant throughout the reaction, I can derive a general rate law, where I have K1, K2, the concentration of alkyl halide and the concentration of nucleophile in the numerator, and in the denominator I have every way that the carbocation intermediate could react. It could return to starting material by reacting with halide at rate constant K-1, or it could go on to product by reacting with the nucleophile at rate constant K2. We could consider two extreme scenarios. One is if the K2 times nucleophile term is much greater than the K-1 halide term. You could control this and make this the case by using a really large excess of nucleophile, making that term larger. When this is the case, we would ignore the K-1 times halide term, getting to a simplified rate law. Then we would see which terms could cancel from here. You could cancel the K2 and concentration of nucleophile terms that appear on both the top and bottom of the equation. And under these conditions, the rate would only depend on K1 and the concentration of alkyl halide. So it is these conditions that we got the original unimolecular terminology for SN1. SN1 reactions can lead to many byproducts, and typically substitutions and eliminations can be in competition with each other, especially in the case of SN1 and E1. E1 specifically refers to a unimolecular elimination reaction. Let's consider the same benzylic alkyl halide as before, and now I'll go through the E1 mechanism. The first step of this reaction would be the same as for SN1, the loss of leaving group. The loss of leaving group would generate a resonance-stabilized carbocation intermediate. The next step of the reaction would still be a reaction with the alcohol solvent, but instead of a nucleophilic attack, a proton transfer can take place to generate an alkene. I would need to draw out a hydrogen at a position beta or adjacent to the carbocation, and I would draw the proton transfer using the base to deprotonate this position, taking the electrons from the carbon-hydrogen bond and using them to form a pi bond. This proton transfer would generate the alkene of the elimination final product. A type of experiment that organic chemists have done is checking for a common intermediate in SN1 and E1 reactions. Let's imagine starting out with a general alkyl halide, where X is some halide, and the first step of either the SN1 mechanism or the E1 mechanism would be a carbocation formation step. One possibility is that the solvent acts as a nucleophile, ultimately generating a substitution product, which I'll call A. Or the carbocation could react with the same type of solvent to undergo an elimination reaction to form an alkene product, which I'll call B. So the same carbocation intermediate could go on to form two different products by reaction with the solvent. What organic chemists have also looked at is what if we have a different leaving group compared to the halide X. This leaving group could leave in the first step to generate a carbocation intermediate. And what you would want to think about is whether or not this carbocation is intermediate to both of these reactions, starting out with either X as a leaving group or Y as a leaving group. If you have loss of the X or Y leaving group to generate a truly the same carbocation intermediate, you would expect both of these reactions to form products A and B, and you would expect that the product ratio of these two products would be the same, regardless of the leaving group that was attached originally. We can also use stereochemical outcomes of reactions to differentiate between SN2 and SN1 processes. In a famous experiment by the chemist Ingold, a chiral alkyl iodide was treated with radioactive iodide anion. I'm denoting the labeled iodide with an asterisk. This reaction was observed to go by an SN2 mechanism and give an inversion of stereochemistry, meaning that the radioactive iodide that was added exclusively as a dash, given that the original iodide was a wedge in this molecule. It's generally observed that SN2 reactions are completely stereospecific, proceeding with this inversion of configuration. And stereospecific refers to the fact that the stereochemistry of the product is controlled by the stereochemistry of the reactant. We can explain the stereochemical outcome by examining the transition state for the SN2 reaction. At the transition state, there is a trigonal bipyramidal geometry about the electrophilic carbon. The regular iodide is departing, and the radioactive iodide is entering exactly opposite the trajectory of the leaving group. And the transition state gives us what we typically think of as the backside attack geometry for the reaction, leading to the inversion of stereochemistry. What's observed for an SN1 mechanism is that partial or complete racemization of a chiral starting material occurs. Let's imagine the following chiral alkyl halide. This is a tertiary alkyl halide that is also benzylic, so loss of leaving group could occur pretty easily from this. Loss of leaving group would generate the iodide anion, and it would generate a carbocation. This carbon is sp2 hybridized and planar, and is not chiral in this intermediate. One possibility is that the nucleophile could come in to the top lobe of the p orbital of this carbocation intermediate. This would generate one stereoisomer of product. Alternatively, a nucleophile could attack the lower lobe of the p orbital, and this would give a different stereoisomer of product. In this case, these molecules are enantiomers of each other, so non-superimposable mirror images. And this ratio of stereoisomers that you form in the products is going to depend on whether or not the leaving group is totally gone, or if it's hanging out close to the carbocation. If the leaving group is well dissociated and well separated from the carbocation, under those circumstances you would expect equal amounts of nucleophilic attack from above or below the carbocation, leading to an equal mixture of products. If instead the leaving group is in the vicinity of the carbocation still, you may not see a complete 50-50 mixture. To end, I want to talk about solvent effects on both types of substitution mechanisms. We're going to imagine polar compared to less polar solvents, and how well those can solvate either the reactants or the transition state. More polar solvents are better at solvating larger charges. So what we'll need to do is compare the charges of the reactants compared to the rate-determining transition state. If the charges are becoming larger or more localized on a single site at the transition state compared to the reactants, increasing the solvent polarity will increase the reaction rate. Alternatively, if the reactants have larger or more separated charges than the transition state, and the charges are becoming smaller and more dispersed at that transition state, the more you increase solvent polarity, the slower the reaction rate becomes. Essentially, under these conditions, the solvent is better stabilizing the reactant than the transition state. What this would look like for case A on a reaction coordinate diagram is, imagine we have a blue line referring to the reaction coordinate using a less polar solvent, compared to a purple line for a more polar solvent. In each case, I'm looking at a single reaction step from reactants to a transition state down to products. Under scenario A, where charges are becoming larger or more localized at the transition state, we have the biggest difference in energies at the transition state, with less polar solvents, making the transition state less stable compared to where you have a more polar solvent. So again, polar solvents stabilize charges. Under this scenario, your reactant energy does not very much depend on the solvent polarity, because the charges here are smaller compared to those at the transition state. So the reaction with the more polar solvent ends up having the lower energy barrier and proceeding at a faster rate. Let's use the same color scheme to consider case B. This is where the reactant is more stabilized by the polar solvent compared to its transition state. Under these conditions, which would be the case if you have a lot of charge in your reactant compared to that at the transition state, your reactant would have a huge energy difference, whether it's in a less polar solvent or a more polar solvent. And the transition state with diminished charge is less sensitive to the solvent effect. By lowering the energy of the reactant in the polar solvent, you end up increasing the barrier, leading to a slower reaction in a more polar solvent. So to determine the solvent effects, you will have to closely analyze the charges in the starting material and partial charges at the transition state to see which scenario you're in. Okay, so this video gave an overview of SN2 and SN1 reactions. I also briefly talked about elimination reactions by the E1 mechanism. I showed curved arrow mechanisms, rate laws, and I also talked about stereochemical outcomes as well as solvent effects. That's it for this video. I will see you in class.